Welcome back. This is the last and final video in this installment on energy profile. Now, in the previous case, we looked at just butane and it was very simple. But to me, it seems simple, but to a lot of you, you would wonder, well, I wish he could have done one more example. And that's exactly what I'm going to do. Okay, but this time, instead of making the second example slightly different than the previous one, I had actually made it a little more complex. Okay, you may think, when you look at this molecule, how can it be so complex? Just wait and see. Okay, we've just added one more metal group to the butane. Okay, and as we begin to draw the Newman projection, around the two carbons indicated by asterisks is what we have. Now, there's probably a zillion questions going through my mind. How do you know which is front, back, and all? It doesn't even matter. Just start with some eclipsed. Okay, as long as you know which ones you're drawing around, it doesn't matter. As you finish the 60-degree rotations, you're going to end up with almost every possible combination. That's the beauty of this concept. Okay, all right, but to go easy on you, traditionally on any exam that you take, even my class or anywhere else, they always give you the starting structure for you in the Newman projection. Okay, or they give you a bunch and then ask you, where does this lie on a graph? Okay, that's usually how this is adjusted. So you may not even have to debate yourself in your mind, okay, I'm only comfortable when it's given front or back. Maybe, yeah, I can see your concern there, but I don't think, if you understand chemistry for what it is, I don't think you have to be worried about it. But again, like I said, this shouldn't be your concern. All right, moving on. We're going to plot energy as a function of angle, just like we did in the previous case. Everything we did is exactly the same. The only thing is your interpretation. One of my previous advisors, when I did both my master's and bachelor's level, used to say, or even PhD used to say, it's not so much collecting data. The instrument gives you the data. What's the big deal? Don't take pride in it. Take pride when you can understand and interpret the data and make meaning out of it. And I think they were absolutely on point. You know, so I'm starting with what is given and I'm doing 60-degree rotation. I'm going to put all of these on the screen. What's the big deal if I can rotate? So what? This is equivalent of me getting data out of an instrument. Well, I've just moved the bond 60 degree each time and I got 7 structures. How do I interpret that? That is the key. Okay, so the data is not that important. Interpreting the data itself is the key. Okay, so we started with number 1. I'm just going to go ahead and label these guys. Number 1, so this is 0 degree. Number 2, 60 degree. Number 3, 120. Number 4, 180. Number 5, 240. Number 6, 300. And number 7, 360. Okay, now there's variance of eclipsed and variance of staggered, which is expected, right? Just like in the previous case, right? So we have one methyl group on one side and 2 on the other side, right? So one of the methyl group really doesn't play a real role as far as determining whether it's eclipsed syn or eclipsed, I guess, it to a certain extent. Okay, because 2 of the big groups without the methyl are on the same side on this one, this would be the eclipsed syn. Okay, if you look at structure 3, that is same as number 1. Okay, so that's also eclipsed syn, and number 7 is also eclipsed syn. So I'm taking the stance of a politician because, I said there can only be one eclipsed syn, but even in the previous case, we saw number 1 and 7 were the same. But I'm going to switch my role from a chemistry person to a politician because I can change my word. So there you go. There can be more than one eclipse in the process. There you go. So I'm a politician now, so I can change my word. There we go. So eclipse syn, we have 3. So we know that eclipsin is the least stable. So let's go ahead and draw our number 1, number 5, number 3, and number 7. So we know they will all be the same high energy. Now number 2, number 4, and number 6 are staggered, right? Now, how do we know which of the staggered has the least within those 3, which is more stable? That's what I'm saying. If you look at number 2, clearly the metal is opposite to a hydrogen, whereas in number 4 and number 6, the metals are opposite to each other, right? But are they different? Is number 4 and number 6, is it different at all? That's my question. Number 4 and number 6, the only difference is as we rotated, the metal is on one side and it's on the other side. So number 4 and number 6 are actually the same structure, just mirror images of it. So between number 2 and these two, we do not have to depict both number 4 and 6, or you can, it doesn't matter to me. On a test, they may not show both. So number 2 is definitely less stable over number 4 and 6. We can also arrive at it 2 different ways. If you notice in number 4 and number 6, there's only one big gauche interaction between the 2 big groups. Okay, all other cases is metal and hydrogen, or hydrogen and hydrogen, which is not a big deal. So there's only one. Whereas in number 2, there's one gauche interaction here, and there's another one here. So 2 is the least stable of the 2 variants of the staggered. So, but it's still more stable than. So 1, and this is 2. And then we go to 3, right? We come down to 4 and 6 are at the same level. They're identical, basically. But let's put 4 here. And number 5. Well, number 5 is eclipsed as well, but it's not fully syn, right? Fully eclipsed, like syn, eclipse syn. So it's slightly more stable than an eclipsed syn. So, but it's not as stable as number 2. So it's above number 2, but below number 5. Okay, and number 6 and 4 are at the same level because they are. We concluded they're identical. Forgive my poor drawing skills. Okay, and then we are at number 7. There we go. So just rewind the video. That's all there is. I don't want to keep extending it and keep saying things that probably will make it confusing. It's a very simple concept, and that's all there is to it. So from an exam perspective, at least from an MCAT or any of the other professional exams, they usually give you the graph and they label the molecules as 1, 2, 3, 4, and they tell you where does 4 fit in, where does 1 fit in, or which one's least stable, which one's more stable. The options are are countless. Okay, so here's my practice. Now, when I took on the idea of teaching chemistry long back, I always made it a point that there has to be times where the student has to work things and be creative and have the opportunity to experiment with the problem. So I'll leave this up to you. Okay, I've given you one structure, rotated 60 degrees, and I want you to come up with 7 structures and draw your graph and show that on your thoughts, and then I'll correct it and let you know if you got it right or wrong. Okay, this is a time for you to practice. Now, you got methyls, you got chlorines. It doesn't matter. The concept is the same. Chlorine is bigger than methyl. So let me give that tip to you. So with that in mind, give this a shot and include the graph and the structures in your thoughts. And this is a perfectly great example to explore your inner critical thinking skills and actually think about the process. All right, well, that's all I had to say about the energy profile for the confirmations, and stay tuned for more videos.